I guess we can move to the next part, which is computer vision.
Let's have time for questions.
Okay.
Yeah. Okay, so there are a few questions here in the YouTube channel, and some of them are they are regarding the morphological inflection task that is posted on our website. One of our one of the contestants is wondering whether following the provided code they couldn't reach the 48.8 accuracy that was stated in the original notebook. Could it be there something that they are overlooking or doing wrong?
Okay,
Any
so
ideas?
I mean, we haven't heard this from other people, so I'm not sure if they are doing something wrong or not, but I think they are more than welcome to reach out to us with email and actually explain the problem they're encountering, and we can of course help them, because I'm not sure if this problem with the notebook, because we didn't have any problems when we were solving it
Mm.
ourselves or the tester users. So
Okay,
maybe
and there is no way that you can know what is wrong with their
with their
okay,
implementation, yeah. So
yes, with
they
their
can always send
implementation.
us, yeah, but they can always send us an email, like even share their collab if they have changed anything in their notebook, and yeah, ask us. Either me or Yova, we will both gonna reply immediately.
Okay, thank you. And actually, it's about the same task. It appears that the warm-up task is not finished. It finishes with end something. So they are wondering whether it's correct or not. And what are the criteria for evaluating the final report, whether the score depends on test accuracy.
I actually now want to open the collab to actually see the deliverables, what it states. But I'm sharing my screen and I don't know where I can find it.
Okay, so maybe you can think about it during the next lecture, and we give more time later to
Yes,
so
because
that you
this
can
is
answer.
yes, because this was the task created by Yova, not me.
Mm-hmm, mm-hmm.
So I mean, I have to check the collab to see. I don't
What's
remember.
in there?
Yeah, I don't remember by heart now, but I'm pretty sure it mentions the deliverables and what is expected. Yeah, I can't find the collab on my. Mm, yeah, I don't have. I'm sharing my screen, so I can't. I unless I stop sharing and try to search the collab. Yeah, should I stop my sharing my screen and look for the collab notebook?
Okay.
Okay. Um, okay, I have it. Um, yeah. So we want you to deliver your code which means that the notebook you have been using or any Python file you have, we want the score, the model accuracy on the test set. And in this task, we would want a report around 300 words describing the changes you made to the model architecture, the data preprocessing, the training procedure. So this means that how we're going to evaluate this is not based on the quality of your code, but based on the results and the approach you used. So how high is your model accuracy is one part that will be evaluated, for example, in this task. And the other thing is how you describe what you did and how efficient is what you did. So I think these are two major evaluation um, criteria, the score and the approach that you use. I hope this answers the question. You can hear me, right? Should I share my screen again? No, I don't know if there are any follow questions. Just replied this question about the morphological task. Yeah, I just highlighted the deliverables and how we're gonna, what is important and we're gonna take into account for the evaluation.
Okay, thank you. People are still wondering about which GPT they can use, which version. Some of them believe that there are parts of GPT-4 and 4.0 that are free and available. Can you clarify that?
So do they mean in general in the final, in the, in what tasks? Because so there are GPT models that are for free, like GPT-2, of course. But the latest GPT-4 models, they are not for free. You can get some tokens from OpenAI by creating maybe an account. They used to give some free tokens. But I'm not sure where exactly we specify the GPT for what tasks they're asking where to use the GPT model. Is this
they haven't specified that, but let's say that everything that is free of charge they can use.
Yes,
right?
exactly. Of course, they can use everything that is free of charge from this Hugging Face platform that we're gonna see in a while. For example,
Okay.
yeah, um, yeah, this notebook uses the T5 model that is based on the presentation we just saw was an encoder decoder model, and it can be found on Hugging Face, T5 Hugging Face, and then it's there, and they can use a T5 model, they can use a GPT-2 model, it's there. I mean, it depends on them, what they want to do, what is the task, but yeah, these are the models that they're going to use, or BERT. Some people, oops.
Okay, thank you. And I think we don't have any more questions for now, so let's just continue with our next lecturer.
Hello, everyone. Hope you can hear me. I will now share my screen. All right. So welcome everyone to this first part of computer vision. In this first part, we're going to cover some more basic topics in computer vision to give you some background. So we'll start with some basic work with images, how we work with images. Then we will extend those operations to convolutional neural networks. We will discuss encoder-decoder architectures through autoencoders. And then I will give you some examples of generative models. Okay, so what is an image? If you look at this black and white image, it's just a table of numbers with a certain width and height. And at each position in this table, which we call also matrix, there is a value which we call the intensity value, which is between 0 and 255 in integers. And each of them, each of those values is an intensity of the light in that particular position, at that pixel. So, of course, for black and white, this is enough, but for a color image, we need multiple channels, so multiple values per pixel. And so we have the common representation that we have is one channel for each color of the RGB colors. So you can see different channels here of that color image that after combined together, we get the RGB. There are many different color spaces, but the one that we use most commonly is the sRGB, and this is how we usually represent our images. In addition, we will have to do some operations on this image to prepare it for an input to a network. And we usually scale from 0 to 255 to 0 to 1. And then we do some sort of normalization, which we call input normalization. What that means is what the network can really benefit from is to have its values centered at 0 with values varying up and down in the range between -1 and 1. So we're going to normalize the image in such a way that its values are between -1 and 1, centered at 0. In addition, different networks have requirements for different input size. So we're going to resize that image. And also, we can use image augmentation. So what a common problem is in computer vision is if you have a fairly small data set, you are going to quickly overfit on it, as you already know from the ML lectures as well. So to have a bigger data set just using the same data set that you have, you can just take one image and change it in some way, like change the saturation, make it black and white, do some blurring on it, all sorts of different operations. So from one image, you get many more images that you can learn a more robust representation while learning. In addition, it's quite common to also do cropping of regions in an image and use it as a separate image. In that case, one image is now a source of many images, right? So there are a few operations that we already mentioned, like, for example, scaling, upscaling and downscaling an image, but also rotation. So we can also rotate the image at a certain angle. But once we do that, the grid that represents our pixels is now not corresponding to the original positions. So all of a sudden, we need to find the color of a pixel that we just transformed, which is in between some of the original colors. So the new pixel is here. We need to know what the color is. And these are the old grid, the untransformed pixels around it. And we need to get the new color. And the simplest way to do this is to take just the closest pixel from the 4, and this is going to be the chosen color. Or with bilinear interpolation is some sort of a weighted sum of all neighbors around it to get the final color. And we call this image interpolation, this process. It's quite common. Okay, so now we are in a position where we can start talking about modifying images. So one way to do it, the simplest way to do it, is to apply a function to each of the values, the same function. For example, we can do things like change of saturation or brightness, as this example is, just additive operation. Now, this is a very simple operation, and if we want to do something more complicated on these images, we would have to do different kind of function to each pixel, right? And to relate the pixels together. So it means just like in ML tasks, you would have to take all the pixel values in one function, and that function will transform all the pixels into something new. But of course, we have a lot of numbers here. We have thousands and thousands of numbers just for one image. So how to solve these huge dimensions that we have to process? Well, one thing to notice about images is they have these spatial dependencies. It means in a very small region around the same pixel, you can find the most patterns on it, and then you can relate different regions of the same image together to get an even bigger representation. And then doing that again and again, you get to the size of the entire image, and you have some sort of an understanding what the image has in it. An operation that can capture such spatial dependencies is the convolution. So to give you an example what it can do, we have this Sobel kernel here. The Sobel kernel is going to extract vertical edges from the original image, as you can see. The whiter, the higher like activation for having an edge there. And how does it work? So the kernel is this small, in this case, 3 by 3 little table or matrix. And we're going to apply it to the image, which is shown in blue here. I'll explain why, but we also pad with zeros. This is mostly to keep the same dimensions after the operations of the image. So how it works is we're going to take the top left part first that corresponds to the same size of the kernel, and we're going to multiply each value here. So 0 by -1, 0 by 0, 0 by 1. And by doing that, we are going to also sum all these multiplications together. And as shown here, since everything is 0 here, we're just going to get the value 0. And for that small region, we have computed that the value is 0. And in that case, it means there are no edges, right? It means 0. Once we move to the right, which is the next thing we do, we are going to have these two different values here. So 10 by 2 is 20 plus 10, we have 30. And that means that we have found an edge. We have found an edge, and this resulted in a bigger number here. So we continue doing that operation over and over until we fill in the entire output matrix here. And it gives us a description where we have the edges. And with convolution, you can do many such spatial related operations. Like, for example, you can blur an image, or you can sharpen it, or you can even do the brightness, the ones that are not spatial, right? The brightness, saturation, you can represent them as convolution. And the idea is now to have a network that is able to learn a kernel. So the kernel will transform an image into a feature map, and the feature map is going to, like as the name suggests, represent some sort of aspect of the image, some feature of it. A feature that is useful for solving the task at hand. So we're going to have a weight for each of the values in the kernel, and these are going to be our learnable parameters. So a convolutional network consists of convolutional layers. It has multiple of those kernels, which we also call filters. It has a certain size of that kernel. Here is 3 by 3, but it can also be 5 by 5 or 7 by 7. There is this padding, and the padding is used since once we do the operation, we're going to lose some rows and columns on the output. As you can see, the top row and the bottom one is lost, for example. And this is why in advance, we are going to fill in with zeros to make sure that we don't lose this dimension. So the output is the same as the input. So we also have this stride parameter, which is just the step size. As you see here, the step size is 1. So we move the square by 1, but we can move it by 2 or 4 or a different number, which is going to result in a smaller feature map, but maybe with some information missing. Of course, we have activations, and we have these pooling layers, which are supposed to reduce the feature maps to smaller dimensions. Because just by using convolutions, we're still going to have a lot of pixels on the output. And we want to process less amount of numbers in the end, because it's computationally expensive. So to do that, we have, for example, the max pool operation, which is going to divide the feature maps in different regions, in this case, 2 by 2. And we're just going to take the maximum value of each region here. So the intuition here is these are activations. These are certain features. And the higher the activation, the more related to the task at hand the feature is. So we just take the activation of the entire region as the highest activation of a feature inside. But there's also other kind of pools like average, which does not perform as well, that well. So we also have normalization layers, which are also probably familiar from the other MLP networks that you have already heard about. But the basic idea is if you have many layers on top of each other, one layer is going to expect a certain range of numbers from the layer below. If this range changes all the time, it is difficult for the current layer to learn properly. So normalization makes sure that this range stays constant during training. Also common is to use dropout layers. They provide regularization. What that means is it is quite easy to overfit on images if training for a long time. And in order to prevent that, we're going to set some of the features to 0. And in that case, the patterns that are part of the overfitting are going to be not there in this particular case where we set it to 0. So it will still have to be an effective algorithm even in these cases. And so far, we have all the components for a network that analyzes an image. But if we want a CNN that can generate an image or manipulate an image, we will need to somehow enlarge the features to an image size in the end. So this is where we use transpose convolution. It is a convolution that is capable of enlarging the input features to a larger space. How it works, just really quickly, is if you take this value from the first value from the feature map that is now input to the transpose convolution, and you multiply it to a kernel, to every value in a kernel, you're going to get a certain result in the end that you can place on the top left side of this bigger output matrix. And if you repeat this process over and over again with all the values, and this square will be moving together with the position, which will take the activation from here, and you sum all of these values together, you end up with output feature map that you're going to use. And this is used quite a lot for like generating the final images, at least in convolutional neural networks. There are also many other kinds of convolutions, but for the interest of time, just move forward. There are many, many, many different convolutional neural networks, but I'm just mentioning the base ones. Of course, there's newer and more efficient than this, but I think really need to know about the base before you continue on the other ones. So VGG is the architecture with first deep CNNs that appeared. And as you can see, it consists of multiple convolutions followed by an activation function. So just the REU. And doing that over and over again, you decrease the dimensions of the features. So you don't have this huge amount of numbers here to process, but now they're processed in a much smaller space. And then you can now just use fully connected layers on top to solve your tasks. Then you have the inception models. It's a family of 4 models, but what is most important in them is they combine different scales of convolutions together. So different scales mean different filter sizes, 5 by 5, 3 by 3, 1 by 1. And in that case, you can create features that are relating multiple scales. So a feature between different scales of patches of images. And that led to quite a high boost. In addition, they're creating this really efficient architecture where they use 1 by 1 convolutions to decrease the filter size, the feature map size, the channels in the end, and many other additional improvements to make a very, very deep network. But when you build a network, a CNN that has many, many, many layers, what you will encounter sooner or later is the vanishing gradient and an exploding gradient problem. It means that the gradient, when you get it lower and lower to the initial layers, can grow really small or really big, which is a problem for learning. It's a problem for training. So to solve this problem, the authors of ResNet introduced those so-called residual connections. So you have a number of layers, and you're going to skip them over with a connection from the input just before them. And you say, the output here will be X plus whatever the output of all these layers is. And in that case, you can propagate the gradient through this skip connection here, through this identity here, which really helps for the vanishing gradient problem. All right, so we move to a little bit of a different topic here. So we have dimensionality reduction. This is a task that imagine that we have a data set with k data points, right? Different entries, many entries. And each of those entries, these data points, have n dimensions. So if you take the examples on the right, you have a certain position on Earth. So you have latitude, longitude, which day of the year we're observing things, and how many daylight hours we have on this day there, and what is the temperature and weather condition. So this is an example of one sample from a data set of many such samples from such data set. So now the task is to decrease those dimensions, those 6 variables, to a smaller number of variables, in this case 3 variables, but not losing the least information possible. And if you think about it here, how you could do that, you have daylight hours, which you can perfectly calculate from the day of the year and where on Earth we are. So you can kind of get rid of that. Once you have many samples, you have the opportunity to learn how to compute this. And you can say for temperature and weather condition, maybe you also can find a pattern given the position on Earth and the day of the year. Of course, you will expect that you will lose some information because temperature varies during different years and weather conditions as well. But this is part of the price to pay for reducing dimensionality. And how this is usually solved, how this task is solved, is you give the input to a method that is going to reduce the dimensions. And then there is a decoder, so a certain method that is going to increase it back to the same dimensions. And you want this reconstruction here to be as close as possible to the input. Now, this is a very simple way to do that. It's a method called principal component analysis. I'm not going to get into the details, but imagine we have a data set of words and we have two variables to represent them. So the number of letters in the words and the lines of the definition in a dictionary. So we have two dimensions and where each of them falls in. So if we have this, then there is this PCA method, which based on eigenvalues and eigenvectors, doesn't matter in this case, is going to find these so-called principal components. So these are, this is an axis that is going to preserve the most information of this data set. What does it mean? It means that if you look at the direction of this axis, the range within where the data falls in on the action is the biggest possible. So if you start projecting words onto this axis, you would have the biggest possible range of values here. And actually, this is a very good way to represent a certain word with one number. You just project the number on the line and use the number that you have, the distance from the zero, as your encoding. And we have encoded two numbers into one. Of course, there will be some loss of information, which would be evaluated by the distance to this axis. So PCA is a linear method, and you also know about another one, which is linear regression. And as you see, just fitting a line to the data is not the best way possible to lose less information. So if you fit a nonlinear function to this data, then the distances will be smaller here, which means smaller loss of information. And how that works is with MLPs, for example. So you give your data to an MLP, which is going to be a nonlinear function now. And this is the encoder. It's going to encode it to this representation here. And the decoder is also an MLP that you're going to learn. So in order to learn, you need the loss function. And the loss function is simply a comparison between the reconstruction and the input. So you want the reconstructed output to be as close as possible to the input. And this is done by mean square error. So you just take the square distances between each dimension here, between each variable, and you sum them together. So how does that translate to images, right? Because we were just talking in general about variables. We are looking at data set with 6 dimensions, right? 6 variables. And now we have an image of around, for an image of 128 by 128, we have 50,000 values, right? How do we encode this? Well, in a very similar way. Instead of an MLP, which we've already discussed to be quite inefficient for images, we will make use of the spatial dependencies in an image by using a CNN. So we're going to give all of these 50 values organized as an image to the CNN, which is going to extract us a very small representation, let's say 512 numbers. And then the decoder, which is again a CNN, will be a reconstruction. We'll give you a reconstruction. And the loss is the same. So this is how autoencoders work for images. In addition, you can make the task a bit more difficult, and you can make the input noisy. So you can add some noise to it, and you have the exactly same task. And the idea is that in the middle, you learn a much robust representation. But this already gives you an idea that you could possibly have different images on input and output. And then it would no longer be an autoencoder, which requires that the same data point to be on the input and output, but the same kind of, the mechanism is the same. So you're going to extract features from the encoder, from the incoming data here, that is really relevant to the task at hand, which is to generate whatever image you want here. And that is the intuition I really want to give here. Now we are going towards a similar but quite a different task, the task of the generative models. So while with autoencoders, you give a specific sample from a data set and you want to reconstruct it, with generative models, while training, you will give images in the training data set. And afterwards, you will be able to give a random noise vector. And this random noise vector, the decoder can map it to a new unseen image, unseen in the training set, unseen anywhere, that is going to be realistic. It's going to follow the distribution of the training data. Okay, how do we do something like this? Well, there are multiple models doing that, and we're going to first start with generative adversarial networks. The idea here is that we have two different submodels, the generator and the discriminator. And the generator's goal is to generate a very realistic image according to the training dataset. And the discriminator is going to try to find out if an image that is receiving at its input is generated or is it real from the training set. So as you can see here, we sample, while training, we can sample an image from the dataset and we can give it to the discriminator and it has to say that this is real data. Otherwise, we take a random noise vector that we give to our generator, and the generator is going to give us some fake data, which is the generated data. And this is also given to the discriminator, and the discriminator has to say this is fake data. So the better the discriminator becomes, also the better the generator becomes at generating realistic data, because the gradients flow from the discriminator to the generator. And what is important is we have this function here that the discriminator is maximizing while the generator is minimizing. So they're playing this game where they will converge to something in the middle, and then there will be the optimum. Okay, but with this method, afterwards, you would be able to only give a noise vector and get an image. But what if you want to have more control? For example, you want to give a certain sketch of an image and get a realistic image of it, right? There could be many different conditions, as you can see here. Now, in order to do that, you just give a condition. This is why we call them conditional GANs. And the condition is given both to the generator and the discriminator. In this way, the discriminator can also check if the condition matches this image. And if it doesn't match, then the generator is not really conditioned on it, right? It doesn't really look at it. And in this way, you receive realistic images, but you can also control them. Now, this is quite an old method. These days, generative adversarial networks are not by themselves used that much, but you will see a lot of use of this discriminator with this concept of a base model and the discriminator playing this game for a more realistic image. It still happens even with some transformer models. Now, another model that is quite used these days is the variational autoencoder. It's usually used for extracting representations of images that then they are passed to like a transformer that works on them, operates on them. So how does this one work? So you have a data set that has a certain distribution. What that means is there is a probability function over the space of all possible images. And for each image, you have a probability. Is this a real image or is it not really likely? So if you get just a random noise, it's probably not a realistic image. But if it's like an image of a tiger like this, you'll get a high probability from here. Now you draw a data set from there, but you will not know this distribution, and you're going to try to build your own here. The encoder is going to take this input image and is going to try to find parameters of a distribution. So this would be the mean and the variance of multivariate Gaussian distribution. And so given these parameters, the claim here is that using this distribution, you will be able to get this image that you sampled from it. And so at the same time, we want to be close to some sort of initial prior distribution. So our model doesn't go haywire and spreads the images all over the infinite space, right? So this is also a small condition that we have. And what the output, what the decoder will do is if I take a certain now code vector from this Wern distribution, so I'm going to sample some sort of numbers that are going to be my representation of the image in this space. I want to really be able to, with a high likelihood, to draw this image from it. If this Z gives me a distribution, I want X to be really likely, right? And so the goal here is to, in training, to maximize this likelihood of maximizing this X being generated by Z, which in turn has been generated by X in the first place, right? While training at least. But this turns out to be intractable. It's a very, very difficult problem to solve. So what they found is, since we want to maximize this, if we find another function that gives us a smaller number than it, then we are still fine because we can maximize this function as well. And this is the evidence lower bound that they have found as such function. And it works quite well to represent images in this way. So how does it work in inference time? We're going to, again, completely get rid of the encoder. And now we have this space here that is already learned, that we can draw samples from it. And we usually pick the initial distribution that we picked. So it would be the normal distribution with mean 0 and variance 1. And then we get a new image. That's how it works. But again, what if we want to have a certain condition? So what if I want an image of a tiger in specific? That means that I need to have some sort of a label, some sort of condition here that, just like with generative adversarial networks, I'm going to give to the encoder and to the decoder. Right? So there we gave it to the generator and the discriminator, and the logic is exactly the same here. I want to give it to the encoder so it knows to put it in a place in this space that it's learning that is related to this condition. And the decoder should know what the condition is, so it knows what to generate exactly, right? So this is the logic behind it. All right, and a version, well, it's quite far from a regular VAE, but it's a vector quantized VAE. And what the concept here is that instead of having, instead of learning distributions over this large infinite space, you instead have a finite set of vectors that you're going to learn. So what this is called is like discretization. So it looks like this. Your encoder is going to produce some position in space, and then your vectors are kind of spread in this space. And based on the distance from whatever the encoder gave you, you're going to take the closest vector or some neighborhood, like a few of them. And then you just take this vector and give it to the decoder. And the decoder should generate a very, very like similar image or the same. And the idea is each of those vectors, while training, they will start representing different kind of images, like different like categories of images. And in the end, like having different distances between them will represent different like a manifold, continuous manifold of images. This method is used quite a lot for building representations of images, as I said before, and then giving it to another model. Instead of giving it thousands and thousands of pixels, now give them just a few features that is going to represent the entire image. And lastly, I want to discuss the UNet architecture. The UNet architecture is an encoder-decoder network that is probably the most widely used these days. It has been used for years. It looks like this, like the picture on the right. And the idea here is that you have a number of downsampling blocks that you can see here, like one downsampling block, another one. It consists of multiple convolutions. So each convolutions will give you more and more complex features after each convolution. And then in the end, you want to decrease the dimensions of this big feature map in the end. So you're going to apply a pool and you repeat again and again and again. And here at the bottom, just like with autoencoders, right? This is an encoder-decoder, you get different input and output, but the idea is the same. You get a very compact representation here of the task-related features on the input, of whatever is important in this image to generate the output image. And then you start the reverse process. It's upsampling blocks here, which instead of max pooling, right, because max pooling is for decreasing, we have the transpose convolution for increasing the size. And what is very important are those skip connections that you see here. So the skip connections, what they make sure is while you decrease the feature size here, you're going to lose some small details from the original image and the features along the way. And if you want to preserve them, you just give the features directly to the block that is increasing your features. So then these small details are still preserved. This is what works best in practice. And UNet has many variants. So on top, you can see some of them, which are mostly related to where the skip connections go exactly. Not just linearly like with the original one, but in some more complicated ways, even adding new blocks in the middle. But an important version of UNet is the one used in diffusion. I'm making a bit of a spoiler from the next lecture here. But the idea is to include an attention layer between those different blocks here. And the attention layer is going to make sure that an input text information is also combined with these image features here. And for diffusion, we have text that tells you what you want to generate in the end. As you just write it down and it gives you an image of it. And this is the part where you connect the text to what is generated. And the same attended features also go through the skip connections here. And I believe that's all.